Welcome back, students, and I think lecture is getting more fascinating, and then as well as little bit more towards some equations, some calculations. So I think that's why I said in the prerequisite you should have studied little bit chemistry and mathematics. So if you do this one, because in the previous lecture I talked about the Beer-Lambert's law and just a very simple equations, but many of the times there is a huge confusion in this one. So just try to read those things and understand the concept about measurement of black carbon and then optical methods or Beer-Lambert's law. Remember, in this is actually I have been discussing because the way I have planned the lecture, it becomes very difficult to just keep brushing things, and I don't like that way of teaching. I want to give the full concepts. So that's why you will see that you are getting many of the lectures on black carbon and thermo-optical or something like that. So because the time is there and we have to make the concept clear. So in this lecture, let's discuss measurement of black carbon using optical method. Okay, I think by now you have been clear. You have been some idea about the measurement of black carbon or elemental carbon and organic carbon in aerosols. And if you just recall, in the previous lectures we discussed there are two methods. One is actually purely optical. In this one only absorption is measured, okay, and nothing else is measured, and this measured absorption is converted into BC mass using a conversion factor. So this is another very important thing. So it is actually used and it is converted. So what is there, and in the previous lecture I talked, because when you are measuring absorption, and if you now remember, just in the previous lecture I said that absorption is a process. So absorption, this, and in order to quantify this one, we define a term called absorbance. We don't talk about the absorption when we talk about the number or in the calculation. So just remember again, absorption is a process, and how much absorption is there, it has to be quantified, then you have to use the absorbance. Or here more technically term is actually used as absorption coefficient. Okay, sorry, coefficient. This is very important. So we will discuss this one because in the previous equations, if you remember, absorbance, this was related to the A is equals to epsilon Cl. This was related to the solution, liquid or aqueous phase. What we are going to discuss this one? This we are going to discuss about the aerosols or gas molecules. Because you know, we assume that in the air, which is actually a medium, particles and gases are there, different particles and different gases. So like when the light passes through the atmosphere, this will interact with the particulate matter, whatever the kind of particulate matter you have. So in the few coming lectures we will discuss about the optical properties of aerosols or optical properties. Then we will see that optical properties are related to the interaction of light with the particles or with the gas. So either it is a gas molecule or in the particles, they interact with the solar radiation, incoming solar radiation or incident radiation. They either absorb the solar radiation or scatter the radiation, and then part of this is actually transmitted. So this process is there. So just remember that when you are dealing with the solution, you usually use this one, but when we are dealing with the gases or molecules, we usually define this one B absorbance, and generally it is written B absorbance. One more thing is actually there, that some places this is also written as sigma absorbance. So and I prefer to use this term sigma absorption but for mass absorption efficiency. So I am not going to use sigma absorbance. I will use throughout the manuscript this as B absorbance and absorption coefficient. Okay, So, I hope this is clear. When I say absorption coefficient, it is related to the absorption by the particulate matter or gaseous species that is present in the atmosphere. So, it is nothing to do with the and when the same thing is dealt in the solution or liquid phase, we generally define at absorbance. Okay. So, the concentration, you will see the equation slightly different. Okay. So, in this lecture we are going to discuss how this absorption was when we measured, then we measure this absorption coefficient, and then through this mass absorption efficiency or mass absorption cross sections we convert it into BC, and this is why the reason is that we usually called small eq BC, because equivalent BC. Okay. Equivalent BC means it is not actually black carbon, but black carbon, if it is assumed that it is black carbon, how much absorption coefficient it will be giving rise to. So, then that is called actually like black equivalent, that is why it is called equivalent black carbon. And I also discussed in the previous lecture that because in the thermo-optical association layer you have actually a thermal methods and you combined your optical method with this one. So, this means this is actually measuring your absorption coefficient or B absorption, and in the thermal method, because when you are putting this in the helium plus 2% oxygen atmosphere, oxidizing atmosphere, you are getting EC. And we also discussed that we generally treat EC is equals to BC. So, this concentration you have, and I told that this is the way it is measured is megameter inverse, we have million per meter inverse 10 to the power minus 6 meter inverse, and then EC concentration or BC concentrations are reported in microgram per meter cube. And this means, now remember, these instruments can directly give that what conversion factor should be there, because which will giving, because EC is equivalent to BC. So, this means if I assume that all the absorption coefficient that I have received here, I have got or calculated is because of the black carbon, or in terms of equivalent elemental carbon, I can calculate that what should be the absorption efficiency of those black carbon particles. And by what, simply by doing this one, how we will get this one, mass absorption efficiency, we just get B absorption divided by EC, we just get this one. So, which method is superior or inferior, I am not going to discuss here, but this method can directly provide you the measurement of mass absorption efficiency as well, along with concentration of EC and OC, whereas black carbon measurement using optical method only relies on the absorption measurement, and then it tries to convert how much absorption is because of the because if there were actually this absorption was because of the black carbon, what conversion factor I should use, I mean mass absorption efficiency. So, usually we use this as a constant conversion factor, which may or may not be true, and then we also use site specific, because all the sites will have different aerosol composition. So, this means you should use different mass absorption efficiency at different sites, but which is not the case, we usually use a constant. So, this is some sort of drawback of athalometer. Yeah. So, before I go, what is that actually? Okay, the animation is somehow inverted. I gave the example of what you call solution phase, that this is the solution that you have, and there is a incident radiation that is falling on this medium, and then you have an I that is going from away from this one. So, part of this radiation is absorbed at this I is given at say particular wavelength, and then part of this is absorbed. Okay, and then we had a relation A is equals to epsilon CL. We also discussed in that one A, we defined that A is equals to minus log of transmittance. Okay, and we defined transmittance as, what was that, I upon I0. This was the equations that we used in the previous lecture. So just remember this one, because there is an analogy I am going to put with these two. So similarly, what is there? This is actually filter matrix. Don't think that this is so much thick actually. If you just see this aerosol filter layer, this is small compared to the filter, but it is not like that actually. So aerosols, and then they are actually of, typically this is similar or because these particles will be embedded in the aerosol. So you can see this one. Now what will happen? You take a punch of this one, a small piece of these aerosols, and so this punch is here, and you put some kind of on some boat or something like that, and you shine a laser on this one. So when you shine a laser, you know intensity I and then wavelength is lambda. So it is shined on this one, and then through this one, so this will, what it will do, it will some part of this one will be absorbed, part of this one will be transmitted. Okay, so you say I, usually it is better to write, I prefer to write I and IT, because IT stands for transmitted, but and I is actually incident, but there are usually the equations write I0 as incident solar radiation and I they use for transmitted radiation. So this is actually this is the very common terminology that we use. So because if you have to define this one, you use this one, for example I and I0. So it is understood that I0 is the incident intensity of the incident solar radiation, or solar radiation, or the laser source that you have, and then I is the transmitted radiation. Okay, so for example here in these equations we will come to this one. So just remember this one. So I and I0. Now what will happen? This part of this one will be absorbed, this one black carbon especially, then remaining part will be transmitted. There will be another process, because this EC particles here black carbon, here black carbon, here black carbon, there are so many black carbon, black spots means let's assume that black carbon. So there are so many black carbon species are there, and they are on each other. Okay, they are on each other. Now what will happen here? So you have one black carbon particle, below you have another particle, and here you have. So when this I0 is falling, the first black carbon particle see the full incident radiation, but now this particle has already absorbed the solar radiation. So the radiation or the energy that is available for the next black carbon particle, will be less or high. It will be less, because it has already absorbed. Okay, and for the third one it will have still lower. So this is actually, so this is called shadowing effect. What is called, actually this is called shadowing effect. And why it is called shadowing effect? Probably because the initial first black carbon is actually making a shadow. So the next one what happens in the shadow, the intensity or the radiation, you can see that it will be decreased. So it is decreased. So in order to account for this one, this shadowing effect is usually written as C. This shadowing effect is generally written as R attenuation. R is a factor, R defined by R. So this is actually, R is usually used as a shadowing effect. So this R value will be less or higher. Now you can tell me here. It will be, R will be less than 1. Okay, because R will be always less than 1, because you are going to have more shadowing particles, and therefore you have to actually increase that one. So the number has to come into denominator. Okay, then another thing will be there. There is a particle, incident radiation is falling on this one, then there is another particle, there is another particle, there is another particle. So what will happen? This particle will see radiation and it will reflect back. and suppose the particle is on the way here, it will see I0 or less, it will not see I0, it will see only the scattered radiation. So, it will again see a less right, okay? It will see a less right, sorry, it will be again this particle, suppose this particle was not there, so they will have only one scattering. But now this scatters again, this particle will again scatter, and if there is another particle, it will again scatter this one. So, this is called scattering effect. So, this means there will be more than one, this will be more than one scattering process. So, this means your scattering has to be accounted for this one. So, actually in principle you should, when you are measuring, there should not be many multiple layers, you should have only one layer, but because you have more than one, so this process is taken care by putting equation C, which is called scattering effect, and C is usually more than 1 because it has the radiation will be scattering with the particle more than 1, and typically the value that we use for quartz filter is C is equals to 2.14. This value is dependent on the particles matrix that you have, filter matrix. There have been many studies, and then it could be 2, 2.14, 2.5, 3, even people have reported different values for this one, but for let's for the complexity and assume this one that C is equals to 2.14. So, you have to write this equation now. So, I hope that you have now got the concept of this one, and this ATN is called optical attenuation. Now, remember this optical attenuation. I defined optical attenuation, and this attenuation is same as a absorption here, absorbance, and you can it depends whether you use 100 or not, because if you are using 100, then it has to be accounted for in the calculation of mass absorption efficiency, but usually if you don't put this attenuation, then you can just calculate these numbers. So, you have to keep on these numbers in the same unit, because what will happen, okay, so how the 100 comes, I will tell you. This actually is attenuation. So, if you just see here this equation, A is equals to minus log of I0 upon I, or log of I0 upon I. So, this is actually kind of absorbance, and if you just remove this 100, then attenuation is nothing but absorbance. You can say 100 is used because in your filters, the filters area will be given in centimeter square, and then volume is given in meter cube. Okay. So, how do you account for this one? Okay, area, because this equations will have area and volume. So, if you don't want to put area and volume here, different units, same units you want to keep, or the number of you want to keep area in centimeter square and volume in meter cube, then you have to put this actually 100. If you are not putting 100, then you have to report this A into meter square and volume in the meter cube. So, that is why the 100 comes. So, now this equation I told B absorptions, I have been discussing that it is absorption and B attenuation. B absorption is absorption coefficient, and the unit is 10 to the power minus 6 meter inverse per meter inverse, and B attenuation is attenuation coefficient. Now, initially when attenuation coefficient is when this shadowing and scattering effect are not accounted for. So, when you don't account for this scattering and absorption signal, the number is called attenuation coefficient. Okay, and this is if you see the way it is written. So, B absorbance will be B attenuation. So, B attenuation will always be more than 1 because you are not accounting for other process, and then you divide by C into R. So, this is a multiplication symbol. There is actually problem with conversion in the software, okay, when it is in the projector mode. So, B absorbance will be written as C into R ATN. Now, and this means you can write B attenuation can be written as attenuation into area upon volume. This is another equation that we have from the previous one. So now remember, you have the equations that we had actually, A is equals to epsilon CL. Somehow down the line your concentration and path length, okay. So this has to be there actually, and similarly these equations will be there, area and volume will come here. So in the concentration you had the volume was given in a liter, here the volume will be given in meter cube, because we are how much air that we are actually measuring or collecting this one, and area will be taken that how much filter that is used for the measuring the absorption signal, okay. And then you do this equation, this calculation. So B absorption can be written as attenuation upon C into R attenuation into area upon volume, their respective units, okay. And so this is absorption coefficient I talked about, and then R attenuation, I said that C is just taken C 2.14 for quartz filter. If you are using other filters, C will vary actually, okay. And R attenuation is given by attenuation coefficient, not attenuation coefficient. This is, what is this one? This is shadowing effect. In order to account for shadowing effect, you have to use this one, and shadowing effect is R attenuation is 1 upon F minus 1, 1 upon F minus 1, just remember this one, and ln ATN minus ln 10 divided by ln 50 minus ln 10. Now if you just remember these equations, this ln ATN minus ln 10 can be written as ln ATN upon 10, and then this ln 50 minus ln 10 can be written as ln 50 upon 10. And if you take these ratios, you can write like this, and this will be ln ATN upon this one. So you can write ln ATN upon 10 but L 50 upon 10. So actually 10 is actually here, because it is assumed that when you have 10% transmission, then absorbance is 1, okay. 90% light is absorbed. So 10% usually you can have for the kind of in the background we use 0% or 10%. So here we have used 10%. At this point actually 10% we assume that there is no shadowing effect when the particles only 10% is loaded actually, in a way, okay. And then if it is more than 50%, then you take, and then if it is more than 50, then you can calculate accordingly. So this equations becomes here, and then you put this parameter ln ATN minus ln 10 upon ln 50 plus 1, and then you add 1. So usually this ratio, this number, if you just calculate this number will be less than 1, and if you add 1 minus, actually it will be in negative as well actually. So it will be negative, this will be a negative number, so it will be 1 plus a negative number, so this number whole R will always be less than 1. So this R value of R will be 1 less than 1, and F is actually, there are different parameters, whether you are doing, it depends on the season, whether you are doing kind of winter season or summer season, and types of biomass burning or other things. So it is also depends on that factor, okay. And then finally you have sigma absorption. This sigma absorption is actually mass absorption efficiency I talked about initially, and if you just write this one, sigma absorption, remember this one, we have discussed this one initially, that sigma absorption is B absorption, which is capital M inverse divided by EC concentration in microgram per meter cube. So you have a unit of meter square per gram here, and when you calculate this one, this is actually like K written, sometimes it is also written sigma ATN, attenuation cross section, or attenuation efficiency, mass attenuation efficiency. So, sigma ATN will be actually mass absorption efficiency into C into R. So, this value will be there. So, sigma ATN will be more than mass absorption efficiency. So, you have to remember these equations, and when you do calculation, this is very basic fundamental equation that is used in the calculation of, okay. And this is where, if you remember my lecture, I said that in the ECOC analyzer, in the previous thermo-optical ECOC analyzer, which keeps on measuring attenuation simultaneously, okay, and it is also measuring EC concentration together. So, from this one you can use to calculate mass absorption efficiency as well as B absorption coefficient, okay. So, these two parameters you can use to calculate. And there is another big problem, that when you say, so if you remember this previous equations, I told in the, just see this one, this in the previous equation I told that attenuation is similar to A, okay, attenuation and A are similar. So, absorbance and attenuation are similar. Don't remember, don't confuse with the attenuation coefficient. So, just remember that absorption and attenuation. So, what was the absorption given, absorbance given there? Absorbance was epsilon CL. So, absorbance was, or this implies, or that both the ways epsilon was proportional to the concentration. Now, here do the same thing, attenuation is proportional to the concentration of what? Elemental carbon. But because you remember here attenuation has unitless, absorbance is unitless, and here we had to multiply it by L, here we do not have to multiply anything. This concentration is reported as microgram per centimeter square, and when you report microgram per centimeter square, this, and if you just see in the equations or the plot, if you just measure attenuation and elemental carbon, this is called surface concentration, for which unit is actually microgram per centimeter. What will happen? What kind of relation you will see? You will see a kind of positive linear relationship, because attenuation is directly proportional to C. So, you will see this kind of relation, okay. You remember this one. So, if this means, this itself tells that validity of Beer-Lambert's law. So, if this equation was not linear, and then this was not kind of valid. So, you have to remember these equations about the calculation of attenuation coefficient and mass absorption efficiency, and I will discuss these things in details in the next lecture, because I think the time is running, or I can take 2 minutes. Okay, let's go ahead and take 2 minutes here. So, this attenuation you can see, and if you see this is the data from Manora peak, and this is the data again from Manora peak. This is actually February to January, you have more data points here, and here this data points is actually, for example, only for December month, so you have lesser data points. But what you see here, optical attenuation, which is actually ATN, is directly proportional to the ECS concentration. And one more thing that you will measure here, if you just extend this axis here, this will pass very close to 0. Similarly, for other extended period of time, this will also be there, but there will be actually some positive intercept here. But if you see similar things is happening at the Mount Abu, you see here linear correlation, and this means that the Beer's law is valid, okay, at the same time, but the contrast is here. If you see, this is Hisar and this data is for Allahabad, you see not so much very strong correlation. At the same time, this actually is not passing through origin, you have some intercept, positive intercept. The same thing is happening here, okay, and this positive intercept means some of this absorption is actually apart from elemental carbon. So, some of the other absorbing species are already there. Some other absorbing species present. So, you have to remember this one, and this is where we get the clue that probably there are actually dust and then brown carbon or Helios-like substances. This was one of the very important study and very important paper, and just see this one, this paper was published in Environmental Science and Technology in 2009. This was my among the first few papers that I was doing. This was actually second paper I published during my PhD paper, PhD thesis when I was doing. So, the point is that don't use the instruments as a black box. Read their actually instrumentation techniques, what it is actually measuring, what is the principle that is using, and you always try to look that can you calculate some other parameter using these numbers, because the instruments, if you can get some other parameters that is calculated, that will always be beneficial to you. So, this is one of the things that I wanted to highlight here, that if you just do this kind of, if you read the manuals of the instruments, and if you read the working principle of the instruments, you may be able to develop something else that is actually not discovered. So, now this method has become a very kind of popular, and many of the people are using this one. And one more thing, okay, so just before, so there was actually a good correlation between EC, and so this means this was suggesting that elemental carbon is a principal absorbing species, and which in a way actually is establishing the Beer-Lambert's law. If there was not actually a good correlation, Beer-Lambert's law was not established, so you cannot do this one, and especially at the high altitude sites, but at the urban sites there was actually some other absorbing species were present. And slope, if you see, slope directly provides the value of mass absorption efficiency. If you just take the slope, this is mass absorption efficiency or mass attenuation coefficient, MAC. They are very different at different sampling locations. So, you see the slope. The slope is very different at all the sites. So, use of the constant mass absorption efficiency value may provide a over or underestimation of BC in optical methods. That is what we were discussing, that BC relies on the measurement of absorption coefficient or absorption or absorbance, and then it converts that if there is actually this absorption is because of the elemental carbon or black carbon, how much absorption, how much black carbon should have been there. So, it uses a constant conversion factor, and this, for example, I did not tell you, this actually athylometer uses 16.6 meter square per gram, this conversion factor, and this is actually also wavelength dependence to 880 nanometer they use. So, we have found that this number is not actually constant, and you have to use different conversion factors. So, I think I will stop here. If there are a few slides, I will discuss those things in the next lecture. Yeah. So, thank you so much. I think this I will finish here, stop this one, and then the next lecture I will see discussion about optical methods. I have discussed now. I have discussed some of the ECOC analyzer and thermo-optical ECOC analyzer. So, this lecture is almost like finished, and now we will discuss more details about the other things that are remaining parts. So, I think there are 2 or 3 units that are still there. So, I have to cover those things up. Thank you so much.